Yeah, thanks for attending my presentation today. This study has been conducted also with Patrick Wallish and has been funded within the same MB program, Smarter Targeting of Erosion Control, and it's actually very related to what Patrick just presented now. Just start with a bit of background about this study. Soil erosion is a national environmental challenge in New Zealand. It's estimated that there are around 200 million tons of erosion each year, and this erosion leads to a wide range of impacts, such as reduction in crop productivity, decrease in soil fertility, water quality, biodiversity, among other impacts. Also, from a policy perspective, we have seen a kind of shift in the focus of freshwater policy from nutrient to erosion. For instance, in the recently released National Policy Statement for Freshwater Management, we have seen that there is now a specific requirement for erosion. And that's basically a reflection or recognition that the main issue in several catchments is actually erosion. So to control erosion and to mitigate this negative impacts, several intervention measures are suggested. But to justify such intervention, we need to understand the cost and benefits of these interventions. So the cost basically is the cost of implementation of such measures, and the benefits are avoiding the negative impacts of erosion. So our study contribute to this benefit cost analysis by trying to estimate the impact of erosion on crop and forest productivity. So on the benefit side of the cost benefit analysis, so the avoided impact of erosion on productivity. So looking to New Zealand literature, we found that there are basically three studies that tried before to monetize the impact of erosion. The first one, which is quite good study by Crosset et al. It's a bit outdated, published in 2001. And basically, Crosset tried to look to several costs of erosion to provide an aggregated value for the impacts of erosion, and he estimated that there are around 127 million. So he estimated that the impact of erosion is around 127 million per year. Diamond et al. 2012 tried to take this analysis one step further by estimating the marginal cost of erosion instead of the aggregated value of the impact of erosion. So what he did that he took this aggregated value, the 127 million, and divided by the total erosion. And he found that the marginal cost is around $1 per ton. There is also a third study, which is quite important, which was done by Barry et al. 2014, and also they focused on the marginal cost of erosion, but they only considered the flood-related impacts, and they found that the marginal cost of erosion is estimated at $6.5 per ton, so a bit higher than what Diamond find. So our study contribute to this literature by focusing by estimating actually the marginal cost of erosion also, but focusing on the productivity related cost and impacts. So to achieve our objective, we developed a framework that consists of three layers. The first one estimate the erosion rates, which was sourced from an erosion model called SeedNet. So SeedNet is a GIS-based model that simulates surficial and mass movement erosion, so both types of erosion. We have also another layer that which is basically around the economic information. So this layer was sourced from an economic land use model called NZ Farm, and it's basically showing the net revenues of different land uses. And to link this economic layer and the erosion layer, we collected data on the impact of erosion on productivity. So basically the physical impact of erosion on productivity. So basically the damage rates, all the yield loss rates, and we collect this from literature. So we try to get these damage rates categorized by erosion type and by land use, so we can link the erosion layer and the economic layer at a bit more detailed scale. So what I'm going to do now, I'm going to show the maps for each of these layers, and then I will present the results and the conclusion. So starting with our case study, so we applied this analysis to a region called Fordel, which is in turquoise color in this map in North Island. And it's basically located in Whanganui district, which is in Manawatu region. Just started with the first layer. So as we said, we had an erosion layer which has two components of erosion or two processes of erosion. It's a surficial erosion and mass movement erosion. So if we look to the map of surficial erosion in the Fordel area, we found that there is a bit high erosion at the northern part of the region with middle rates of erosion in the middle part and almost no erosion at the southern part. So that's basically because the southern part is flat land and the northern part is kind of sloped or hilly land. So that's why, we expect that there is more erosion in the north, and it's decreasing when you go south because you are moving to more flat land. Overall, the erosion rates in this area was quite low compared to the national rates of surficial erosion. So moving to the second type of erosion, which is a mass movement erosion, and looking to one of the types of mass movement erosion, which is landslide, we find that the area is suffering from a lot of landslides. So it's basically covering almost the whole area except the southern part. And if you look to the northern part, there's kind of a circle which has quite low landslide erosion, and that's because this is covered mainly by plantation forestry. So that's why it's kind of reduced the landslide erosion. And I will show later in the next maps the land use and how this is related to the erosion. This is second type of mass movement erosion, which is called gully erosion, and you can see that it's mainly located in the northern part of the area with some patchy spots at the corner of the middle part of the area. For the earth flow, there was really small areas which suffers from earth flow erosion in the northern part. Moving to the economic layer. So that's a land use map of the area. So the greenish areas are basically exotic pine trees or native trees. So we can see that the northern part is highly covered with plantation forestry and a little bit of native forestry. The orange color is sheep and beef. So it's basic. So some of the northern part and middle part is basically sheep and beef. The red color is dairy. So there is small patchy parts in the middle and south, which is more flat, of course. So it has a bit of dairy. And the southern part of the area, it's more horticulture. It's mainly arable and a bit of vegetables. And that's because it's flat. It's quite flat and suitable for arable and horticulture plantation. So in terms of income, most of the income of this, so if you look to the left of the table, most of the income are generated from arable, which is around $8.5 million, and also from exotic forestry, which is around $7.5 million, and dairy, which is $5.7 million. On a hectare basis, we found that the highest income are generated from vegetables, which is around 9,000 per hectare. and also from fruit, which is 7,000 per hectare, and dairy, which is around 3,000 per hectare. The lowest income per hectare was from sheep and beef, which was only $7 per hectare. Also forestry, plantation forestry is not much, it's around $600 per hectare. So to link these three pieces or three layers together, what we did that we tried to rescale the erosion rate to fit into the damage rates that we found from literature. And then we assumed that the productivity loss is kind of linearly related to profit loss. So basically giving you an example, say if in a specific pixel in this map, there is say erosion rate of 200 per hectare, 200 ton per hectare. So according to our rescaling rule, this 200 ton might be reflected to be equivalent to say 20% rate of yield loss or productivity loss, and then we assume that profit loss will be also 20%. So this rescaling decision tree rule will differ according to the land use and according to the type of erosion. So as you see in the bottom part of this slide, here we assume that if it's pastoral land, dairy or sheep and beef, and it's surficial erosion, then the range of damage to productivity is between 0 and 69%. However, if it's mass movement on pastoral land, then it's between 0 and 78%, and so on and so on. So we have for cropland and we have for forestry different ranges, whether it is surficial or mass movement. So in each pixel, we define what type of land use, what type of erosion here. We get this erosion rate and we translate it to damage rate according to this rule, and then we assume the profit will be the same like the productivity loss. So we did this process for all the pixels in the map, which is which we did on a 1 hectare basis, and then putting this three pieces together, we get this results, which is basically showing the marginal cost of erosion. So the first column is showing the land use in this area. Second column showing the marginal cost of surficial erosion, so the cost of 1 ton of erosion. The second column showing the marginal cost of mass movement erosion, and the fourth or final column showing the aggregated marginal cost if you add surficial to mass movement. So from this table, if we look to the last column, the total marginal cost of erosion, found that the minimum cost of the minimum marginal cost was in sheep and beef, and it was $0.003 per ton, so that's almost zero. And the highest one was in vegetable farms, and it was estimated at 3.93, almost $4 per ton. So there is quite a big range here. The mean of all this marginal cost of erosion in all land uses is $1.2. So that's a mean. We also found that the marginal cost of surficial erosion is higher than the marginal cost of mass movement erosion. So if you compare the values between the second column and the third one, the surficial and mass movement, for example, if you look to the last row, the vegetable, the surficial is $2.81 per ton, while the mass movement is only 1.12. And that's mainly because mass movement processes leads to a higher amount of erosion. And given that we assume kind of similar rates of productivity loss, then you end up with higher marginal cost for surficial compared to mass movement. So we can also plot the results in this table as a map in spatial, so we can visualize the results. And basically, you can see that given the land use and erosion rate, some parts which has a darker color, which has a higher marginal erosion cost, and some part has a lighter color, which has lower marginal cost of erosion. And it's basically, I mean, if you look to the middle part, it's basically because there is a lot of sheep and beef, and it has very low profit, and that's why the marginal cost of erosion is quite high, is quite low. Yeah, so so next steps in this analysis. So basically, just takeaway messages. So we what we said that what we found that the marginal cost of erosion range between $0.003 per ton and $3.93 per ton, with a mean of $1.2 per ton, quite similar to what Diamond. The mean is quite similar to what Diamond et al. Found. However, this is only for productivity impact. Diamond assumed the $1 is for several types of impacts. We also found that the marginal cost of surficial erosion is higher than the marginal cost of mass movement erosion. And for future steps, we are planning to include another type of impact. So besides productivity loss, we also want to consider the marginal cost of erosion on water quality and maybe other types of impacts, I don't know, like biodiversity or other types of impacts. We also want to incorporate uncertainty in the model. So this damage rates and how the scaling was done, and also maybe exponential relationship between damage rate and erosion. So basically, when you get higher erosion rate, you expect higher damage, not really a linear relationship. So there is still some work need to be done, within this relationship. Think how to link these three layers to make it more robust. And yeah, we're planning to do this in the upcoming months. Yeah, thank you.
Thank you, Tarek. Are there any questions from the field?
I actually have two questions.
Yes, please, yeah.
So you link erosion to productivity and profit loss, and you distinguish between the surficial and mass movements.
Yes.
What type of policy implications do you think your work may have? This is my first question. And the second question is, in your future work, you said you plan to incorporate uncertainty. So how do you plan to incorporate this to your work?
Yeah, so from policy perspective, as we said, so when you, for example, as a policymaker, you want to implement a intervention measure to reduce erosion, like, for example, plantation forestry or whole farm planning or fencing streams, or whatever measure you want to implement, you need to you are imposing cost on the farmers, and also there is a cost for the government to implement these measures, and you want to justify that this specific intervention. So you want to show that the benefits from implementing this measure is higher than the cost of the measure itself. And as we said, the benefit of the measure is basically avoiding the adverse impact of erosion in this area. So by estimating the marginal cost of erosion, you could basically highlight one of the main impacts of erosion, which is reduction in in productivity. So you can show that, yes, okay, we are implementing an expensive, say, riparian buffer, which will cost $100 per hectare for the farmer, but at the same time we are reducing the impacts of erosion. One of them is productivity loss, which is around around this amount. So we are basically justifying your intervention to the public, to the farmer, and to the policymaker. So that's the first question.
I have one question before. Sorry, I realize I'm jumping in before the second question gets answered. But a real quick follow-up to that, Tarek. Something that maybe we didn't consider. I'm wondering what the results are basically saying is that you should focus erosion control efforts on areas with high value farming and in areas with high areas of erosion, right? Yep. Is that basically what we find, is that, if you're a policymaker, you want to go into fruits and vegetables because they have a higher profit per acre or hectare than other places. And so given that that's kind of what the results say, have you looked into the data at all for where these places occur? Do these high value products occur in high erosion areas, or are they mostly in low erosion areas?
Yes, so it's I think so. Our map is basically motivated by higher incomes. So for example, I mean, it's, of course, it's a combination of both, right? So it's combination of erosion rates and farm incomes. But for example, if you look to this map, in the middle part on the left side, there is dairy, I think, in this area, which generate quite high income, 3,000, and there is also relatively high erosion in the middle part compared to the southern part, which has really high income, vegetables or arable, I think, arable, yeah, but lower erosion rates. So, yeah. So I think it's mainly driven by profits and secondly by erosion rate. And one of the things we actually want to do is assuming this exponential function of between erosion and productivity loss. So basically saying the marginal cost of erosion at lower rates of erosion should have lower impact on productivity compared to higher rates of erosion. I don't know, it's a bit complicated, but what I want to modify is this linear function between erosion rate and damage on productivity, to reflect this point better, that when you have pixel with very high erosion, the higher rates of erosion will have higher impact on productivity. Yeah, it's not very clear at this point, but yeah. But to summarize, the answer of your question, yes, it's based on both, as you said, on farm income and erosion. But so far, it's dependent more on farm incomes.
Okay, and then I believe the second question that Celine had asked was on uncertainty and how we plan to incorporate that.
Yeah. So for uncertainty, we first it's basically around this rescaling rule, and we assume now according to land use and according to the type of erosion, we'll have a range of damage rate. So this 0 to 69% or 0 to 78%, and we want to add an kind of error term to this range, kind of random error term, so which reflect that we are not really certain about these values. We just it's point estimates from literature, and there is a bit of uncertainty around this rate. So we want to add an error term with specific distribution, hopefully to reflect this uncertainty.
Thank you, Tarek. Are there any other questions?
I had one. I've just put a comment in the chat. Sorry, it's Blair Keenan here. Just the extension that you were talking about to the effects on water quality. I think that would be really interesting from a policy making perspective, because those external costs are almost more important in terms of a policy intervention. And I'd expect them to show quite a different pattern. So, for example, the avoided costs that you're showing here are really low on those, the high country, which would be typically sheep and beef farming. But those, you'd probably see a much higher mass load in the water bodies from that. So I think that would be a really useful extension from a policy-making perspective.
Yeah, I definitely agree about this. The only issue that actually, I think there is very few or scant studies around the impact of erosion on water quality. So, yeah, as I said, because the policy, previously in the last maybe few years, the focus of the freshwater policy was more on nutrient rather than really erosion. So you can find kind of a few studies that try to estimate the impact of nutrient on water quality, but there is really almost none. There is no studies that try to estimate the impact of erosion on water quality. So part of this project, Patrick has conducted a kind of survey, non-valuation, non-market valuation technique.
Yeah,
So,
if I could just
yes,
just let me
yes,
jump
please,
in really
Patrick.
quick,
Yeah.
Tarek. Yeah, the one area that might be of use is Tarek and I and a few others. We did some stuff on erosion for a sediment rule for MFE, and in that project we used NIWA did some modeling recently that links sediment loads to clarity. So there's a bunch of non-market valuation studies that estimate the impact of clarity, using stated preference methods. And so we're trying to release a new one of those ourselves. But this will at least allow you to connect sediment loads to values. But yeah, then I think you raise an important point though, is that how easy is it to get nutrient leaching from these sheep and beef farms into that equation? I think that's a really important point though, because those are the areas that will have a lot of this leaching and a lot of the sediment going to the water bodies. So do you guys have a good way in Waikato of doing that kind of linking for, when it's a pasture area to get kind of what's going into the water body from there? Maybe not. Yeah. But no, I think you raised an important point though, because if you use this approach, then you'll get one distribution, right? Focus on high value farming. And that only might be a very small part of the story when you're looking at total erosion and total environmental impacts.
And also because it's the the avoided cost for the land user, they already have an incentive to do something about that themselves. So there's less reason for a policy intervention for that.
Yeah, that's actually a really, really important point. Thank you very much for that. I think we've basically about reached our time for these two. We're, there's only 2 presentations in this session, so if anybody has any burning questions, I'm happy to stay on and catch up. But otherwise the next set of sessions starts at 10:45.